Hello everyone and welcome to the flight thermodynamics subject. Today I'm going to solve an example for you to see how we can uh, calculate the efficiency for a Rankine cycle when we use different methods to improve its efficiency, or we are going to see how the effect of the uh, modification of the Rankine cycle. Here we have a steam power plant which is operating in ideal Rankine cycle. The steam enters the turbine at 3 megapascal and its temperature is 350 degrees Celsius, and it is condensed in the condenser at pressure of 10 kilopascal. We need to determine A, the thermal efficiency of this power plant by this information and also the TS diagram which we have here. B, the thermal efficiency if a stream is superheated to 600 degrees Celsius instead of 350 degrees Celsius. If you remember, this is one of the methods to improve the efficiency of the Rankine cycle. The steam is superheated and its temperature is higher than the part A of the question. And part C is the thermal. We need to determine the thermal efficiency if the boiler pressure is raised to 15 megapascal while the turbine inlet temperature is maintained at 600 degrees Celsius. This is also is another method to improve or increase the efficiency of the Rankine cycle. And we have already introduced this cycle to you and this modification to you. And here also what we have is the TS diagram for all of these three different conditions. First, let's go and see how we can find find the answer for part A, which is the thermal efficiency of these power plants. Okay, now let's see how we can find the thermal efficiency of this cycle, which is the Rankine cycle. Here we have TS diagram of this cycle, and also we have information about some information about different states in this TS diagram. First, let's see how we can to find the thermal efficiency of this cycle. We need to know the properties for all of these states in this cycle. So let's start with state 1. If you notice here, state 1, it is on the saturated liquid line. So we need to find its enthalpy, and also we need to find the other information related to this state. What are the information which we have for this state 1? As you notice here, it is constant pressure line. So in state 1, pressure is also is P1, which is 10 kilopascal. And also, as I told you, we know that this line is this state is in saturated liquid line. Okay, now by this information, let me just write this. With this information, we need to know how much is the H1 and how much is the specific volume as well. How we can find this information from a TS diagram or from the property which we have here. If you remember, we use different thermodynamics table to find these characteristics for water with these with this pressure, and also with this information which is in saturated liquid line. So let's see how is the procedure to use these thermodynamics tables. Here you can see the different tables which we can use to find the properties for the water with different characteristics, as you can see here. But if you notice here, we have different tables the table A4. These tables also can be found in the end of your textbook, Essential textbook. You can find these tables there, and I will upload in Kalam, and you can easily download the PDF file for these tables and uh, use them to find the thermodynamics characteristic of the water, especially for this chapter. So if you notice here, we have different tables. Table A4, uh, again another table which is also table A4, but it is different. Table A5, as you can see here, all of them is for the water. But if you remember from the thermodynamics subject, we have different phases for a substance. So we need to know characteristics for a substance according to its phase. So these tables, table A6 for superheated water, table A6, as you can see here, it is a long table, and table A7 is for compressed air, compressed liquid water. So you can see these tables are prepared according to the phase of the water. Here in our cycle, in Rankine cycle, usually we have the different phase as well. These phases is in the TS diagram, and you can recognize the phase of the water for each state of the TS diagram uh, according to the position of that state in the TS diagram. Then according to that position, we can come to these tables and select the appropriate table to find the characteristic. Here, as I said, we need to find the H as the enthalpy of the working fluid, which is here is water. We need to find H for that state. But which one of these tables we should use to find these characteristics? We have a method to understand or to recognize which one of these tables is appropriate. So let's see what is the method and what is the guideline to understand which one of these tables should be used for our purpose to find the characteristic or properties of the water in different phases. Okay, now we are in the table for to find the properties which we need, which are the enthalpy for state 1 and also specific volume for um, that state. So what are the noun here is the pressure at that state, which is 10 kilopascal, and also we know that the water in this point or this state is saturated liquid. So let's see which table we can use. As you can see here, because we have saturated water as well here, just we can use this table. But to use this table, we need to know the temperature of the liquid or water in that state, which we don't have here. What we have here is pressure. Let's see which table we can use here. Again, it is for saturated water, but still we don't have the, here also we have temperature. Let's see about the next table, table A5. We have saturated water. It's okay, the first condition is satisfied. And also you can see here we have the pressure as well. You can see here the pressure here is 10 kilopascal, which is for saturated water. Also we have saturated water. And we need to know how much is H. If you notice here we have 3H, H for saturated liquid, for evaporated, and also for saturated vapor. The H which or enthalpy which we are going to find is this one, HF, because also we know the state is saturated liquid, which is 191.81 for H. This is H1. in our example, H1 is HF and its value is 191.81. How about the specific volume? Also, that can be found here. For saturated liquid, again, for this pressure, we have this much for the VF, which is 1. And by this method, we can find the properties for state 1, which are the H1 and V1. Okay, now we went to the table A4 and we found the values for H1 and V1, and which we know that if you are for the pressure 110 kilopascal actually, and we have or specific volume for saturated liquid at 10 kilopascal. The value for these two properties are 191.81 kilojoule per kilogram, and also for VF is this much. We found these values from the table. Okay, so for this is for state 1. What about state 2? You know, this process 1 to 2 is in the pump. So the process is, from these two states is equal to work which is uh, required for the pump or pump in work of the cycle. For state 2, the information which we have is, first of all, we have the pressure for state 2, P2. How much is it? It is 10 megapascal, because you know in TS diagram this line is the isobar line, so the pressure in entire this process or this line will be identical or same or constant, which is 3 megapascal. So we know how much is the pressure in the state 2, and also we know how much is the entropy for state 2. Why? Because entropy of state 1 and state 2 are identical. You can see here S for both of them is identical. So we know this information as well. S1 is equal to S2. This information also we can get from the cycle which we have here. Okay, now how much is the work for the pump or W pump in is, if you remember, we had an equation to calculate the W pump in. When I introduced you the energy flow in the Rankine cycle, we had this equation which was this equation V1 times P2 minus P2 minus P1. Okay, so, and all of this information which are in this equation we have, V1 is equal to this much, 0, 0, 0, 1, 0, 1 cube meter per kilogram. And also we have P2 and P1. P2 is 3 megapascal, P1 is 10 kilopascal. Do not forget to convert the unit of the pressure here. We should have one unit, same unit for both of these two pressures. So P2 is 3 megapascal, means it is 3000 uh, uh, kilopascal minus here 10 kilopascal is P1, like this. You can now, if we solve this equation, the result of the calculation for this equation, which is W in, will be equal to 3.02 kilojoule per kilogram. Now, how we can find H2 or enthalpy in state 2 by using this equation, which I think it is, you know, this equation because we had this equation in the previous slide as well. So W um, uh, in, so H2 or enthalpy at state 2 is equal to uh, enthalpy in state 1 plus W pumping or the work which is done in the which is received or it is done on the pump. By substitution, the value for H1, which is 191.81 plus the work which we have calculated here, the result will be the amount of H2, which is 194.83 kilojoule per kilogram. So now we have calculated H2 or enthalpy for state 2. Next, we have to go for state 3 and calculate enthalpy for state 3. Okay, now we reach the state 3. Let's see how we can find the enthalpy for this state. Uh, if you notice, state 3 is in superheated area. This is so for state 3. It is in superheated area or region, and the information which we have is its temperature, which is temperature in this point is 300 uh, degrees Celsius, and also we have the pressure for this point, which is or P3 is 3 megapascal. So we have this information. So now we have to find H or enthalpy for this point, and also we need to find entropy and also other characteristics for this point. Again, to find these characteristics or these properties for the working fluid in this state, we need to refer to the thermodynamics table. But which table? Let's see which table we can use for this state. Okay, here again we have this thermodynamics table. Let's see which table we should use to find H and S enthalpy and entropy of the state 3. As I told you, the state 3 is in a superheated region. So first of all, we should find the table for superheated water. The table A4 is for saturated water, so it is not useful for us. Let's see about the other tables as well. Uh, Again, saturated water, A5 saturated water, A5, and table A6 is for superheated water, which is the table which we are looking for as well. Okay, so let's see what we have this table. Here we have temperature. So these properties, V, U, H, S as a specific volume, internal energy, enthalpy, and entropy of the water in different temperature is present. But if you notice also, we have these properties in different pressure as well. So to use this table, we need to know both of the temperature and pressure of the water in that superheated region. So here the temperature which we have is 350 degrees Celsius, and pressure is 3 megapascal. Okay, here we have, as you notice here, we have the temperature 300 and above, but the pressure is not 3 megapascal. Okay, let's see, find the 3 megapascal pressure here. Okay, it is here. This column is for the 3 megapascal pressure, and also if you look at the left side, you can see the temperature here. So here temperature is 350, and also for this pressure is 3 megapascal. We need to find these characteristics. If I just go a little above, you can see here the first column is for a specific the first column is specific volume. Let me just cover this like this. So here H is or enthalpy is 3116.1 kilojoule per kilogram, and also we have entropy in state 3 with this condition or this characteristic, which is 6.7450 kilojoule per kilogram Kelvin. So by this method, we can find the values or the enthalpy and entropy for state 3 in this table. Okay, we found the H3 and S3 enthalpy and entropy for state 3. Let's just write down their values. H3 is 3116.1 kilojoule per kilogram, and also S3 is 6.7450 kilojoule per kilogram Kelvin. So we have also H3 and S3. We know the properties of the working fluid, which is water, for state 3. Okay, let's go for state 4 and see what are the information which we have for state 4. If you notice, in stage 4 we are in the mixture region. Here we have a steam which contains some moisture, but the information also which we have for this point is the, first of all, S3 is equal to S4 here, as you can see. S3 and S4 are identical, and moreover, we know this is in the mixture region, so we can write this equation. If you remember, also we had this equation in previous example. We can write like this: x4 equal to s4 minus sf divided by sfg. If you notice in the tables, we have the entropy. This is for the saturated liquid. This is for saturated mixture or vapor in this region. We have uh, these values, and we can calculate, in point stage 4. We have also the uh, pressure. Pressure, as you can see here, is 10 kilopascal. So we know it is in this region. So with this information, which P4 is 10 kilopascal and the state is in the uh, saturated vapor area or mixture region, we should go to the tables again and see if we can find this SF and SFG for state 4, because we have a state, we know how much is the entropy for the state 4. is equal to the S3 we have here, 6 point something. So we need to go to the table, and for this pressure, find the SF and SFG. After, when we find these values, the after we find this value, the SF and SFG, again we can write another equation to find the value for H, which the equation is like this. We will use this X to calculate H. H4 is equal to HF plus X4 HFG. We can use this equation to find H4, because also we can find HF and HFG for the state 4, which is in the mixture uh, region. Okay, now again we are in the table, thermodynamics table, to find the properties for a state 4. But what we have for state 4 is the pressure, which is 10 kilopascal, and we know it is in the mixture region. So we need to again use table A4 or table A5, which is for saturated water. As you can see here, table A4 is for the temperature, and we can find the properties like the enthalpy, entropy, internal energy, and specific volume for the water when we have the temperature for that state. But here what we have is the pressure. So we need to go to the table, which is for saturated water, and according to the pressure for that state. The pressure which we have here is again 10 kilopascal, similar to state 1. And here what we need to get from this table or record from this table is uh, Hg, HFG, and uh, actually HF and HFG, and also SF and SFG. So we need to have these values, or when the all of these values, we need to have these values, record them to be used in our calculation. So we need to use uh, this information in this table, the entropy and enthalpy. To first, we need to use these entropy values for this pressure for the saturated water to calculate X. Then by using that X, we can calculate the H according to the equation which I showed you, and also we will back to those equations. So let's go to the equation, substitute these values which we have for S and H, then find X, and finally find the enthalpy or H for state 4. Okay, now we uh, found the required information to solve this equation. We have S4. Here we have S3 is equal to S4, so just we substitute it values. It's 6.475 minus SF we found from the table, so 6492 divided by, and also we found SFG, which was 74996. After calculation, we will find the value for X4, which is uh, 0.8228. This is value for X4. Then by substitution of this X in this equation, we can calculate the H4 as well. So just let substitute the values for HF we found from the table 191. 81 plus X4 we have here 8128. times the HFG, which we found from the table, 2392, 2392.1. So after calculation, H4 will be 2136.1 kilojoule per kilogram. So we found H4 as well. So up to now, we have found all of the uh, properties for the working fluid, which is water, in four different states. And also, if you notice here in also if you notice here in the uh, graph, the process 4 to 1 is for Q out of the cycle, and the process 2 3 is for Q in. So to calculate Q in and Q out, Q in is equal to H3 minus H2, the change in the enthalpy of the working fluid before and after boiler here, and Q out is equal to H2 H4 minus H1, which is in this process. By substitution of H3, H2, H4, and H1, which we have already found them in previous steps, we will have these values. Q in will be equal to 29.3 kilojoule per kilogram, and for Q out, its value will be 1944.3 kilojoule per kilogram. So we have calculated the Q in and Q out for these Rankine cycle as well. And the last step is to calculate thermal efficiency of the cycle, which, as you know, thermal efficiency, or eta TH for the cycle, is equal to 1 minus Q out divided by Q in, which we have calculated both of these two parameters. 1 minus 944.3 divided by 29.3, which will be 0.334, or almost 33.4%. So thermal efficiency of this Rankine cycle with the configuration and structure which is shown in part A of the question will be 33.4%. In step B and C, we will see how the thermal efficiency will change if we change the some of the parameters in the cycle. Okay, in part B of the question, it mentioned that if we change the temperature of the working fluid or water in state 3, which is in superheated region, then how will be the thermal efficiency of the cycle? So here in this case, as you can see, state 1, 2, and 4 even, state 1 and 2 does not have not changed, and the changes is for state 3 and 4. So we can write for part B of question state 1 and 2, no change compared to the part A of the question. And for state 3, as you can see here, you know, in part A, this T3 was 350 degrees Celsius. So now it is changed to the 600 degrees Celsius. So the characteristics or the properties of the working fluid in this state is changed, and we need to find the properties for the working fluid here with this characteristic, which T3 is 350 degrees Celsius, and the pressure is uh, again 3 megapascal. And we know this is superheated. So again, we need to go to the thermodynamics table, and for superheated water, find the H for this state according to this characteristic. If you go to the uh, here, sorry, I made a mistake about this temperature. Temperature is 600 degrees Celsius. So temperature is 600 degrees Celsius, different from the part A, and also the pressure is same as the part A of the question. And we know also this is superheated water, so we need to go to the table, thermodynamics table, and find the enthalpy for state 3 in the superheated uh, table with this information. Temperature and pressure is now. If we go to the table, we will find the value for H3 equal to 3682.8 kilojoule per kilogram. I'm not going to show you again the table. The same procedure for superheated uh, water. You can go to the table and find this value for the point state 3 in part B of the question. And what about point 4? With same procedure like part A, we need to calculate the uh, H4 as well. So we know how much is the S3 from the H3 from the table for superheated. So now we can also find S3 from the table. From the table, we can find S3. I'm not going to calculate this part here. We need to find x4. If you remember, the equation for this was S4 minus S4 divided by SFG. Why we can use this equation? Because again, if you notice here, S3 is equal to S4, as you can see here. Then we can write this equation to find x4. If we go to the table for superheated water, and with this information find S3, then S3 is equal to S4. So we have S4, and also we can find the SF and SFG for water in with this information which we have for 10 kilopascal. Again, like previous step, for 10 kilopascal we can go to the saturated table and find SF and SFG by substitution of the values for SF and SFG, and also by knowing the S4 from this step, we can calculate x4, which for part B, x4 is equal to 99,915. So we have x4. By using this x, we can calculate also the h4. So h4 again here, we can calculate h4 by this equation, h4 hf plus x4 hfg. So again, for state 4, because we have in the saturated, we are in the saturated region. Again, we can go to the table A table for saturated water with pressure, because we know how much is the pressure. Pressure is 10 kilopascal with same procedure like part A. We can calculate. We have X4, we have HF, we have HFG for 10 kilopascal saturated water. We need to have HF, HFG, then we can calculate H4, which is 2380.3 kilojoule per kilogram. This is H4, so we have H3 and H4. Again, we need to calculate Q in and Q out for part B. Q in, again, with a similar procedure like part A, we can calculate Q in and Q out. Q in H3 minus H2, Q in, and this is condenser Q out, and which H3 and H2 we have. H2 doesn't change, and H3 we have calculated here. With H2 we have from the previous steps, part A of the question. So by substitution of H3 from here and H2 from part A of the question, we just substitute them. Then the result will be per kilogram. And also for Q out, we need to calculate H4 minus H1, which is 380.3 minus, which will be 21.4. Again, similar to the part A, we need to calculate thermal efficiency for this part, which, if you remember, the equation was this one. We have both of the Q in and Q out. By substitution of their values, we can calculate this thermal efficiency, which is 373 or 37.3%. And if you notice here the thermal efficiency is 37.7% compared to the part A was 33.4%. You can see here by increasing the temperature of the superheated steam, we can increase the efficiency of the cycle. About 3%, the efficiency or thermal efficiency of the cycle is increased by increase the temperature of superheat steam in the cycle. Next, we will see the answer for part C of the question, and we'll see how is the changing of the pressure effective on the cycle efficiency. In part C of the question is mentioned that the pressure also in the boiler will increase to 15 megapascal. If you remember, in part A and B, the pressure in the boiler was 3 megapascal. Here also the pressure is increased, and you can see here the temperature of the superheated water or a superheated steam in state 3 is also 600 degrees Celsius like part B, but higher than the temperature of this state in part A of the question. Let's see how we can calculate the thermal efficiency for this cycle. Okay, first of all, we should know how much is the enthalpies. You know, we need to follow a same or similar procedure to find the enthalpies, then Q in and Q out of the cycle, and finally by using the equation which we had for thermal efficiency we can calculate the thermal efficiency for this cycle. But before that we need to know how much is the enthalpy for all of these four states. For state 1, if you notice here, again we have saturated liquid, saturated liquid. Also, if you notice here, the pressure P is 10 kilopascal. So for state 1, nothing changed. So for state 1, it is similar to part A and B also. So we don't need to calculate or to find H1. It is already known and we can find its value from part A, B, and A of the question. What about the state 2? If you notice in the state 2, which is here, the pressure is changed. The pressure in the state 2, because it is in the saturated water area, and the pressure here P is 15 megapascal, and also if you notice here S1 is S2 4.2. So with this information which we have, we can also calculate the enthalpy for state 2. Now we are going to find the enthalpy for state 2. If you remember, because here also we need to find the enthalpy for state 2 with a similar procedure like what we have in part A. So for state 2, again we need to use this equation. W pump in is equal to specific volume at 0.1 times P2 minus P1. We had this equation. This is because of the, this process 1 to 2 shows the process for the pump, and if you notice it is W pump in. So the change in the enthalpy of the working fluid in the pump before and after that will be the equal to the W of the work of the pump, and we can calculate by this equation. We know how much is P2. It is 15 megapascal or 15,000 kilopascal, and we know how much is P1. It is 10 kilopascal. What about P1? If you remember, for the state 1, we had H1 and V1 in part A. They have not changed also for this part C of the question. So we just, I'm just going to write them again here. And also V, which was 1. Okay, so we have V1, and simply by substitution of V here times, do not forget to convert 15 megapascal to 15,000 kilopascal minus minus 10 kilopascal. It will give us the W in the pump after calculation of the multiplication and the subtraction. Okay, after calculation of this equation, the result will be 15.3099. Then if you remember also, we had this equation H2 equal to H1 plus W pump in. And if you just substitute the values, we have, forget to the unit for this one. If we just substitute the values for these parameters, H2 will be equal to H1, which is at 191.81 plus this much for pump in work or pump work will result will be 206 point almost 95 the kilojoule per kilogram. This is the enthalpy for state 2 we can calculate by this procedure which I show you here. So we have calculated enthalpy for state 2. Let's see how we can calculate enthalpy for state 3. To find the enthalpy for state 3, first of all, we should notice that the state 3 is in the superheated area. So this is the first thing we should notice, and also we know how much is the temperature and pressure for this state. So again, we can go to the thermodynamics table for the superheated water or steam and find the enthalpy for the superheated steam with temperature of 600 degrees Celsius and with pressure of 15 megapascal. So the information which we have here is for state 3. Let me just write it down here. State 3, first of all, superheated. T is or temperature is 600 degrees Celsius and pressure is 15 megapascal. So with this information, we need to go to the table, thermodynamics table, and find the T and P, find the enthalpy for this state as well. Okay, now we are in the thermodynamics table. We are going to find the enthalpy and also entropy and other properties for state 3 of part C of the question. So we know how much we are in the table A6 because it is for superheated water. And also if you notice here, we should find the appropriate pressure, which is 15 megapascal. And also we know how much is the temperature for superheated water in this state is 600 degrees Celsius. So the information which we are looking for is in this row for this state. The enthalpy is this much, 3583, and also the entropy we can find here for superheated water with this pressure and also with this temperature. So table A6 is the table which we should go and find this information. Okay, so from the table we found how much is the H3, which is equal to 3583.1 kilojoule per kilogram. So we found the enthalpy also for state 3. Now, what about state 4? For state 4, if you notice here, state 4 in the graph is in the mixture region. So to calculate the enthalpy for this state, we need to go to a similar procedure like a step B and also step A to find the X or fraction of the steam, then calculate the enthalpy by that. And also for this state, we should notice, let me just write it down here. For state 4, we need to find x, which again we can use same equation which we had for this one. Let me just recall the equation here. The equation was here you can see x4 is equal to s4 minus sf divided by s4. Let me just erase this. So s4 minus f divided by sfg. After we calculate x4, we can simply find h4, which is h4 equal to hf plus x4 hfg. Then what are the S4 for this state? Similar to the previous uh, parts of the question, S4 is equal to S3. How we know this? From the figure which we have here from the cycle, S3 is equal to the S4. So S3, again, we need to go to the table, the place which we found H3, also we can find S3, and it is also equal to S4. By substitution, that value here, we will have S4. What about the SF and SFG? If you notice in for X for state 4, what we have here for state 4 is its pressure, which is 10 kilopascal, and we know it is in the saturated water or mixture area. So state 4, the pressure or P4 is 10 kilopascal also for part C. So we need to go to the uh, table for saturated water and find SF and SFG, and also HF and HFG for the this state for saturated water. But we already know how much is the the SF and SFG, and also HF and HFG, because this state is not changed in part B and also part A. So this HF and HFG, or enthalpy of the saturated liquid and also saturated and also the for the mixture region is identical with the part B and part A. The only differences is the S4 here, if we compare this equation with the previous steps. So by substitution of the S4, which we can find from this step, from this step we can find S3A as well, where we find H3. Also there was S3, so we can have S3 as well, and we have also SF and SFG and HF and HFG. Then by substitution of the information which we have from the table, this X4 will be equal to this much, which is 0.804. This is the value of X4 for the part C of the question. By substitution of this X in this equation and this HF and HFG, which you can find in the previous steps, we have already calculated. We found these values H4. If you can see here, HF 191.81, and also HFG is 2392.1. So we have already found the HF and HFG. So by substitution of their values in this equation, we can also calculate H4, which is equal to the 2115.3 kilojoule per kilogram. So we have also enthalpy for state 4. Now we have all of the enthalpy, so we should calculate Q in and Q out for the cycle presented, which is presented in the part C of the question. So Q in will be equal to H3 minus H2. Same like the previous step, we can calculate this Q in and Q out. We have H3, H2, H4, and H1. By substitution, we will have their values, which is equal to 3,306.2 kilojoule per kilogram. And also for Q out, we will have 1,923.5 kilojoule per kilogram. Okay, now we need to calculate the thermal efficiency. Again, with same procedure, we can calculate the thermal efficiency of the cycle. We have both of them, Q in and Q out. Just substitute them in the equation. We will have the efficiency, which is 43 or 43% will be the efficiency. You can see here the effect of the increase in the pressure of the boiler. So you can see here the pressure when we increase the pressure of the boiler and also the temperature, both of them simultaneously, you can see here the efficiency is 43%. Compare this efficiency, thermal efficiency, with part B and C. In part B, if you remember, it is just 37%, and in part A was 33%. So you can see how these the two different methods can improve the efficiency of the Rankine cycle. This example, the purpose of this example was to show you how much will be the change, the difference between the thermal efficiency of different cycle, Rankine cycle, by changing the superheated steam temperature or the changing in the pressure of the steam in the boiler, or simultaneously both of these methods. You can see here the maximum thermal efficiency for the cycle is when we increase the superheated temperature and also the pressure in the boiler. Thank you very much for watching this example. I hope it helped you to solve more problems.